next section of Chapter 5 is dealing with lipids. This is a very diverse group of biomolecules, and they have a lot of similarities to carbohydrates in that they're largely constructed of carbon, hydrogen, and oxygen, those three essential elements that we've covered before. They are largely used, at least within animals, as an energy storage molecule. So there's a lot of similarities there. But the big difference, or one of the major differences between lipids and carbohydrates, is the fact that they are largely hydrophobic. They have no affinity for water. This is a great thing for animals because animals are largely composed of water. We're a big sack of water, about 75–80% water. And so if we're going to have a massive energy storage molecule, we need it to be available to us at any point in time. And we need to be able to stash this molecule wherever we can for when it's needed. And so lipids are stashed throughout the body, and they are fats, they are oils, waxes, steroids, and these molecules are, again, the primary long-term storage molecule for energy in animals. Within plants, there is an energy storage component, but there's some other functions within plants that lipids are used for, and we'll talk about that later. Fats are composed of two smaller molecules, or two parts. I don't know that they're necessarily smaller, they're components of the whole, but this fatty acid molecule certainly is not small. It's a very long chain molecule, and we'll show you a diagram of that here in a second. The glycerol molecule is kind of the cap that holds these fatty acids together. And again, the diagram that is on the next screen will make more sense. This glycerol molecule is a 3-carbon alcohol. It has a hydroxyl group attached to each carbon. We've talked about hydroxide groups as our functional groups in Chapter 4. The fatty acid is, again, this very long carbon skeleton, and this is where the energy is being tied up in the molecule. And on the screen here, you can see this chain can go on for thousands and thousands of carbons in length, as can this chain, as can this chain. And hopefully you can see now why these are so valued by animal bodies, because look at all that energy. Look at all those chemical bonds that can be used for energy storage. And again, most carbohydrates are going to be in rings or simple chains, branch chains, and they are going to be significantly smaller than what we're seeing here with these fatty acids that are attached to our glycerol molecule. This is the glycerol, and the fatty acids then are linked to that, and that gives us a triglyceride. Tri means 3, and the 3 fatty acids are where that name is coming from. Also, quick side note here, we have a dehydration reaction taking place that we've talked about previously in this section on carbohydrates. The hydroxides are getting rid of the water to link that fatty acid to the glycerol, and that creates the synthesis of this fat molecule. You can see a little bit more up close here. Fats separate from water, again, because of the hydrogen bonds that are tying these fatty acids together. The 3 fatty acid chains are joined to the glycerol molecule. Again, this is called a triacylglycerol, or triglyceride for short. And again, this would be the picture that we had up on the previous screen. When you hear about fatty acids, lipids, fat molecules, oftentimes you hear about it in terms of fatty acids, saturated fatty acids, or unsaturated fatty acids. And again, the difference is in the bonding. Saturated fatty acids have the maximum number of hydrogen bonds. Every carbon is loaded up with single bonds, and if it's in a chain, you're going to have carbons linked to carbons, linked to carbons, linked to carbons, but you're also going to have hydrogens filling out the rest of those 4 bonds. The difference is in an unsaturated fatty acid is we have taken out some of those hydrogens and we've replaced them with a double bond between the carbons. This picture here is, well, actually we want to skip over that and move to this picture here. We have incorporated a double bond into this fatty acid, and what you notice right away is that that double bond has bent the chain. That is a distinctive characteristic of an unsaturated fat. The fatty acids get all bent in different directions, which means that they're not going to layer themselves in such a way so that they're nice and stacked on top of one another. This stacking that you see in saturated fats is largely why you have a solid at room temperature. The stacking allows for hydrogen bonding, which allows for these molecules then to be linked into the solid form. When you have all this bending taking place, it is a lot more difficult to stack these molecules and get them organized into a solid structure. Therefore, most of your unsaturated fats are liquids at room temperature. So there's a big difference between our lipid molecules. And when we're talking diet, we're talking about butter, we're talking about animal fat, you know, like the fat you'd find on a steak. Those are all part of the saturated group. Fish oils, canola oil, vegetable oil, those are largely going to be under the category of unsaturated. What's better for you, eating saturated fats, eating unsaturated fats? You need some fat in your diet, and it probably doesn't hurt to have a little of each. Right now, scientists, researchers are kind of arguing about this, and they've been arguing about it for 20 or 30 years as to which is better for you, which is more healthy. So for right now, I think moderation for each one is probably the smartest way to go. One thing that you can say medically, that if your diet is rich in saturated fat, and again, what I'm saying is moderation, you shouldn't be overdoing any one of these, but if you are eating a lot of saturated fats, what you find is because of the fact that these molecules are hydrophobic, you're going to, and your bloodstream is 75% water, you're going to run the risk of having these fatty molecules depositing on the walls of your blood vessels, forming what we call a plaque, which would be a narrowing of the blood vessel, which could, of course, lead to clots, strokes, heart attacks, and therefore you really want to kind of pay attention to how much saturated fats you are getting in your diet. Hydrogenation is the process of converting unsaturated fats to saturated fats, and again, you know, the hydrogens are being forced into that fatty acid to pull, you know, get rid of that double bond. Trans fats contribute more than saturated fats to cardiovascular disease. That's why you see so many products in the grocery store labeled with no trans fats. Again, that's where this is coming from. These unsaturated fatty acids are not synthesized in the human body. They're manufactured or produced in a different way. And oftentimes, let's start that over. Okay. Go back, talking about trans fats and how they may contribute more than saturated fats to cardiovascular disease. So you really got to be kind of careful about the amount of trans fats that you're getting in your diet. This is why you see so many different products in the grocery store labeled as no trans fats. It's a big marketing push to get you to buy their product, and they're doing it for health reasons. They're kind of pushing the envelope a little bit to get you to buy their stuff, but it is an important thing to keep in mind. Certain unsaturated fatty acids are not synthesized in the human body, and therefore we really should be trying to supplement them in our diet. So, you know, you gotta, again, moderation is what we're talking about here, not eating too much of one and supplementing what we're not getting on the other end. And these essential fatty acids oftentimes are the omega-3s. You hear about these every now and again in the news or in advertisements for different products on television, and these fatty acids are actually important for normal growth And many scientists believe that they do actually protect against cardiovascular disease. So instead of causing cardiovascular disease, which many of your unsaturated fats will, these actually are believed to help prevent. So that's part of the dispute between what's better for you, saturated, unsaturated. It's a discussion that's been raging for quite some time in the medical profession. The major function of fats is energy storage. We talked about this in class, that this is a huge molecule. Your body loves these molecules because your body really doesn't understand that there's a grocery store right down the street and you can go buy food at McDonald's or wherever. Your body thinks in terms of caveman times. We don't know where the next meal is coming from, so we're going to pack away these molecules for a rainy day in case we can't club an elk or a deer over the head and get a meal. So we have a large amount of adipose tissue, which is made up of adipose cells, which are specially designed to stash away fat, and that is where these molecules are stored throughout the body. Phospholipids, we talked a little bit about. These are very important molecules. We will talk more about them when we get into the chapter on the cell membrane, because this is largely where we discuss phospholipids. Phospholipids, instead of having 3 chains of fatty acids, have 2. One of the chains is replaced with a hydrophilic head. This phosphate group that you see right here is incorporated for one of our fatty acid chains, and that gives us this distinctive molecule that on one side loves water and on the other side hates water. Why is that important? Well, if we're going to build a cell membrane, we need a way to bring water to the cell membrane but not have it just running in and out like crazy. The movement of water has got to be controlled within the cell. And so these phospholipid bilayers, again, we'll spend more time on this later, are created in such a way where we can bring water to the membrane in case we need it, but we don't have it just running like crazy in and out of the cell. Same thing on the other side. Inside the cell, we can bring water to the membrane if need be, and then again, we can't have it just running wherever it wants to go. So we need controls built in here, and that's where the proteins come in, and we'll be talking about those in a little bit. Steroids, this is another class of lipids. These are characterized by a skeleton consisting of 4 fused rings. There's a diagram on the next slide here. Cholesterol is a very important steroid. There's good cholesterol, there's bad cholesterol as you get older and you go to the doctor and you get your annual checkup. That'll be a major component of what they're doing with your blood tests, trying to evaluate what your cholesterol levels are. Again, what they're trying to figure out is, are you a candidate, an at-risk candidate for heart disease, cardiovascular disease, stroke, heart attack, and those cholesterol levels in your bloodstream are going to be a key indicator. Here are those fused rings that we were talking about previously. This is a molecule of cholesterol, and you can see we got some methyl groups and hydroxide group as we review our functional groups. And that brings us to proteins, so I'm going to stop right here.